Okay, I guess it's time to start. Okay, so good morning everyone, and now we just finished our chapter 2 on determinant on Monday, and now starting a new chapter. This is probably the most important chapter of the whole course, and now we are going to start talking about vector spaces. Okay, so the vector spaces are the are the core part about studying linear algebra. Today we are going to see what's the meaning of being linear and what's algebra. Okay, and we start with reviewing high school maths again. So we starting define those Euclidean vector spaces. Euclidean vector spaces, they have this notation R to the n, where n is an integer, natural numbers 1, 2, 3, 4, 5. And this just means n-dimensional space of with real coefficients. Okay, so for example, R2 means R2 is a space of these two-dimensional vectors x1 and x2. Okay, and they can be and this two-dimensional vector can mean some a point from a line segment from 0, 0 to 1, 2, like this. Okay, and we say two line segments, so two vectors are equal if I have the same length and direction. Okay, and yeah, so it's in picture like this. So those are vectors that we draw on two-dimensional plane. So we have this x1, x2 vector, and it can point from 0, 0 to x1, x2. Or it can point from AB to A plus x1, B plus x2. Okay. And here are more examples. For example, this 2, 1 vector can point from 0, or it can point from 2, 2, or can point from minus 1, minus 1. Okay, so vectors are just those line segments with some length and some direction on a plane. And there is a length of vector, and they are calculated by square root of x1 squared plus x2 squared. So it's x1 squared, x2 squared, and the length here is square root of x1 squared plus x2 squared, and this is calculated from the Pythagorean theorem. Okay, and now we start doing something more interesting. So given a vector, we can multiply it with some scalar. So this is a scalar multiplication of R2, and we are going to see a lot of scalar multiplication today, but we start with the easy one. So we multiply a vector with some scalar alpha, so alpha is just a number. We define it as you just multiply both coefficients by alpha. So for example, if your x is 2, 1, then you can multiply by minus 1. When you put minus here, we mean multiply by minus 1. I guess we should emphasize. Okay, this is going to be tricky later, but for these R2 vectors, this just means minus 1 multiplied by your x. Okay, and you and so this is, you put a minus sign on everything, so it's minus 2, minus 1, and you times 3, it becomes 6, 3. You multiply by minus 2 is minus 4, minus 2. And here are those drawing pictures. So we have our vector x, that's a 2, 1, and you multiply by minus 1, you multiply by 3, or you multiply by minus 2 are those vectors. And you see you multiply by something that's bigger than 1, you can stretch it in the same direction. You can multiply by some negative number, and you go to opposite direction, etc. And okay, so this is the first operation you can do on vectors. You can multiply them by some scalar number. Then the second thing you can do is you can sum two vectors together. So you have some vector u and some vector v. U is this with the two coefficients u1 and u2, v with some coefficient v1 and v2. Then you got u and v as this vector that has coefficient u1 plus v1 and u2 plus v2. And geometrically, you can draw like this. And so you have u here, and you place a v where the starting point of v is the end point of u, and so you place the v here, then then this line from the start point of u to end point of v will be u plus v. And you can also do this in different order. You can do v first, then u first, then u second, and that will be same as this u first, v second. Okay. So both of these are u plus. So this is u plus v, and then you can also have w equal to w equal to u minus v here, because u plus w here become v, so you move things around, you see that w equal to v minus u. Okay, and so these are two-dimensional vectors. You can sum in together, you can multiply them by a scalar, and then we can generalize these to R3. Okay, so R3 are just vectors with in 3 dimensions. So you have x1, x2, x3, and R3 are vectors that pointing from 0, 0, 0 to some point x1, x2, x3. And you can also do addition on R3, etc. And now let's generalize this very quickly. Now we fully generalize to Rn. So now if n is bigger than 3, then it's really hard to draw, because we live in 3-dimensional space, and we don't really know how to draw something in 4, 5, 6 dimensions, etc. But we can still write down an algebraic expression. So every vector in Rn we can define it as so vector in Rn can be defined as, I guess, x in Rn. Actually, I will say this is something like x1, x2 to xn. Okay, and then we can still also define scalar multiplication and addition on Rn. And yeah, just like what you expected. So you multiply by some scalar alpha, then you multiply every coefficient by alpha, and then you add together 2 vectors, you add together every coefficient of the 2 vectors. Okay, so those are this is vectors in Rn, and their scalar multiplication and addition. And also, I guess we can say a little more. So something we'll not use today, but later on we'll check this. We'll go back to this. Later part of chapter 3 is the length of vector in Rn. So the length of some x will be n-dimensional Pythagorean rule, Pythagorean theorem. So that's summation x1 squared plus x2 squared all the way to xn squared. Okay, and taking square root. Okay, so that's Rn. And then there is another vector space that's not quite important as Rn, but we'll use a little bit. So let's talk about it. That's I guess more generalization of Rn. So that's the vector space of M times n. So it's a vector space related to M times n dimensional matrices. And we think them as a generalization of Rn, because we think Rn is a vector space, is a space of this vector space Rn can be think of a set of n by 1 matrices, and with real entries. So the things inside Rn are those n by 1 matrices. So those vectors. So those vectors, because we just think vectors are n by 1 matrices. Okay? So we think things inside Rn are n by 1 matrices. Then we think about, can we have a vector space for general n by n matrices? And indeed, we can have a vector space for n by n matrices. So we can think about, well, this set of n by n matrices with real entries are definitely a set. But for vector space, we want something more than just having a set of things. We also want, as we'll see very soon, we also want scalar multiplication and addition. Okay? And so here we define the scalar multiplication and addition, and they are what we expected from matrix algebra. And so we have addition of 2 things inside Rn by n is is defined by you just do matrix addition. Okay, so sum of a plus b is just c equal to a plus b, and if you write down the elements, you have cij equal to aij plus bij, and also also you have scalar multiplication. You just multiply every entry by multiply every entry by alpha. And I guess from this notation, you see that from what we have in what we have on Rm times n, Rm times n is really similar to Rn with just different dimension. So you can think Rm times n is just Rmn. So you can just put so something in m times n is coefficient put in block, but you can just rearrange them and into a really long vector with length mn, and yeah, so with this definition here, m times n is really I guess homomorphic to Rmn. Okay, where I didn't define what's homomorphic, but you just think there is some one-to-one correspondence. Okay. Okay, so that's a very quick review about Euclidean space. And any question? If no question, then let's totally switch a tone and let's do ultimate generalization, and let's go to abstract vector space. Okay. So so we have Rn that is a vector space, and it has scalar multiplication and addition, and we want to generalize the concept of vector space to any set that has addition and scalar multiplication. Okay? So this is a very abstract definition. So you can have a set of really anything, and define these two operations. You want addition and scalar multiplication, and we say that if those three things, so this set and those two operations, satisfy some rules, there are actually 10 rules, then we call it a vector space. Okay? And so first there are two rules, so those are C1 and C2 rule. You need to, they are called C because they are closure property. So first, this set need to be closed under those two operations. And so you want that you take any two things outside of, so we do C2 first. So you take any two things from your space and add them together. They should also become something inside your space. Okay? And then it's the first thing is that you multiply a scalar with something inside your space, then that should still be something inside your space. Okay? So it's called closure because the end result is you are always still inside your space. Okay? And here, I guess here we do this very general, so alpha can be anything, but for now we will think about alpha being real. Okay. So yeah, in most of the course, alpha is real, but I think alpha mostly real in this course. But in the later part of the course, I think we will talk a little bit about what happens when alpha is a complex number. Okay. For now, we can just think alpha is a real number. Yeah. I guess, yeah, we didn't really say alpha is a real number here. Okay. Anyway, so this is the definition of the abstract vector space. So first, we need to satisfy the closure. And now this is the linear part of why this course is called linear algebra. Okay, so those two operations where you do addition and scalar multiplication, those are usually called linear operations. And remember that we already see something very similar to this. We already see those linear operations, and they are the row operation on matrices. Okay, so recall we have the row operation matrices. Okay, so row operation 2 is you multiply your row with a scalar, so it's like the scalar multiplication. And row operation 3 is you add a row to another row, and with the multiplication of other with some number. And so row operation 3 is like you do scalar multiplication and then you do addition. Okay, so yeah, those are linear operation. And as you probably already see from we're talking about this here, so later on we are going to analyze our matrices as something related to a vector space. Okay, but yeah, that's something we'll do later. For now, let's focus on this linear space. So we have addition and scalar multiplication. These two operations, and we want our space to be closure. And but we cannot just define addition and scalar multiplication as any operation. And so for our space to be a vector space, we need a lot of rule for the addition and scalar multiplication to satisfy. Those are all satisfied by Rn, but yeah, we want our abstract vector operation to also satisfy all those axioms. Thus, I guess go through them one by one. First one is that the addition need to be commutative. Yeah, so x plus y need to equal to y plus x. Yeah, so if you think the plus as a plus sign for usual say scalar plus or Rn plus, these things are very obvious. But remember, we're defining abstract abstract operation here. So we define something operator something, then the left and right don't always commute. Remember, so for example, we have A matrix multiply on B not equal to B matrix multiply IA. So in general, if you define an abstract operation with two input, then the left input and right input might not commute. So we need this commutative here. And so first one, we need this. And second one, we still want our plus to be like the plus we think about in scalar. And so we want associative rule for our plus. So you x plus y first, then plus z, that should equal to x plus y plus z first. Okay. Yeah, so plus should be just like our scalar plus. And then for the vector addition, we want it to have a 0 and inverse. So first we define 0. 0 element is something that you have some vector, then plus 0, and you go back to your same element. So you want yeah, so this is the definition of 0 element. And so for all element in your vector space V, you plus 0, you go back to same thing. Okay. And so this is 0, and we also want to define inverse. Okay. And so this is inverse minus x, so we denoted inverse as minus x, and it's the thing that so everything has an inverse. It's a thing that you added to your thing, and then you get back to this 0 vector. So you need to define F0 if you with S3. So this 0 vector is this 0 vector. Okay, and yeah, and now we have some trouble with our notation. So it's important to remember here that this 0, it might not be seen very clearly, but we have both face 0 here. And so both face 0 don't equal to scalar 0. Okay, so this is very important, as we'll see later. So the both face is symbol, is not scalar, it's not number. So this is actually a vector. Okay, so I guess let's put an example. So for example, in R2, then this is both face 0, and it's really hard to draw here. I guess let's try to draw both face, but I might give up and just draw a vector sign later, although that is different from our notation. So anyway, in R2, both face 0 equal to this 0, 0 vector. Okay, so it's another number, it's a vector of 2 dimensions, just both coefficient being 0. Okay, and so as both face 0, and there is a minus x. Okay. Yeah, so those are rules with addition. Then now we go into scalar multiplication. Then we want scalar multiplication on vectors just like scalar multiplication on scalars. So we want distributed rule in two different ways. So alpha x plus y should equal to alpha x plus alpha y. And alpha plus beta x should equal to alpha x plus beta x. And those are all for all. Yeah, I don't know why. Sorry, I keep changing words, but all I mean here is for all. Okay, and this is also for all. Okay, that's make the notation consistent. And yeah, so those are alpha. So scalar multiplication should be like scalar multiplication for scalars. And so we have a distributive rule and also associative rule. Okay, so alpha beta x equal to alpha times beta and times x should equal to alpha times beta x. Okay, and finally we have a weird rule, but it will be, as we'll see soon, that is actually very important. That is 1 times 0, 1 times any vector equal to the vector back. So 1. So the scalar 1 times x equal to x for x inside your space. Okay, any question? And yeah, so let's have more notation. So x, y, u, v are vectors. So just like before, we have those both face later as vectors, and I guess this is a bit of overuse of a notation, but it's okay. So this is the same notation as column matrices that we have before. Okay, so as column vectors. So that's because usually when we think about vector, we usually think about column vector, but for now those are abstract vectors. Okay, and so yeah, both is a small case number. Those are vectors. It's the same notation as column vectors, but yeah, that's what it is. And and then we have the small case number, either English or Greek numbers. So alpha, beta, or AB, those are scalars. And yeah, as we say, the scalars are real numbers most of the time. Okay? And V is the set of things. Okay, so set of all those vectors. So universal set. V is, I guess I should not really say universal set. So V is it's a set. It's a set, but I guess I should say set of vectors. Okay, set of vectors in your vector space. Okay. Set of vector in vector space. And but sometimes you will also just call V the vector space. Although technically, then there is a nuance about whether addition and scalar multiplication is inside V or not. But anyway, so V is the set of vectors, and they are also the vector space. Okay, and then finally, as we said, both face 0 is really different from just plain face 0, and 0 is a 0 vector, and then this is 0, then this then this simple 0 is a 0 scalar. And yeah, so both face 0, say in Rn, is a 0, 0, 0, 0, 0 vector. Okay, so yeah, so we can define a whole bunch of different vector space, and so we give any set V and give two operation, addition and scalar multiplication. Then we can check whether it's a vector space by checking all those 10. So I guess we really need to check 10 things. Okay, so we need to check the two closures are satisfied and the A axioms are satisfied. So let's start with some example. We have our space. We don't actually call V. So I guess here I should not say V also. So it's either usually it's capital case letter and starting from something on the later part of alphabet. So V, W, U, etc. Okay, U, V, W, etc. Those are the space or set of vectors. Okay, and yeah, so here the W is our proposed vector space. So W are set of row vectors where it's a 2-dimension and where the first element is anything. So but the second element is 1. Okay? So we think about this W, and we make some addition rule and multiplication rule on it. Okay? And since it's a set of matrices, we just have a matrix addition and matrix scalar multiplication as the addition and the multiplication on this set. And they want to see whether this is a vector space. Okay. So first, we have, so we check a closure C1. So first we check a closure C1. So we want to see does any alpha multiplying on W make it still inside W, and we see that on the first rule we check it already failed. So you multiply some alpha with the matrix multiplication rule on some vector A1 in W, then it's alpha A and alpha. And so if alpha don't equal to 1, this is not inside W, then W is not a vector space. So the W is not vector space because it's not closed under scalar multiplication. And similarly, if you add two things inside W, so A1 and B1, and you have this A1 plus B1 using matrix addition rule, then you get A plus B and a 2, then this is not inside W again. Okay. So you see that this W with matrix addition and matrix scalar multiplication, the addition and the multiplication is not a vector space. Okay, so and but you can think about a further question. So what kind of addition and multiplication rule will make a W a vector space? Does anyone want to answer? Can you can you make a W a vector space by defining a different scalar multiplication and a different addition? Want to answer? Well, if not, I will leave this question hanging, and maybe you can come to me to tell me about your answer later, and let's prove the next theorem. Okay. Guess we will finish this, and yeah. Okay, and this theorem is a property about 0 and the inverse of vector space. And so this gives you a taste of what abstract algebra do, because those theorems are really obvious in Rn. Okay, but the hard part is we now define our vector space with all those very abstract rules. So we have these two rules and these 8 rules. Okay, and in particular we define our 0 and inverse in very abstract way. We have those two definitions for 0 and the inverse, and we don't really say what's our 0 and what's our inverse. Okay, and so now we want to relate our 0 and the inverse to the scalar 0 and the scalar inverse. Okay, and this is what so you see the property here is what we stress a little bit when we talk about R2. So in R2 minus x, so the inverse of your vector is just minus 1 multiplied on your vector. But if now you have an abstract vector space, then this is not obvious. And also 0 times 0 vector equal to 0 vector is also not obvious. And and in particular, so there is even something more fundamental you need to prove for your 0 and the inverse. So first we need to prove our zero and the inverse are unique. Okay? Although technically you can kind of combine the proving side. The proof of one is a bit more complicated because it's really, you need to prove two things. So what we want to do is first we want to prove zero is unique, and then we can prove 0 times x equal to 0 vector. And also we want to prove the inverse is unique. Okay, so let's stress the unique a little bit here. So we want to prove it unique because in our definition we didn't say the 0 and the inverse is unique. We just say there exists one. Okay, so there exists an element such that this happens. So there may be other elements that this also happen. Okay, and but we want to prove unique, and so I guess let's go straight to the proof of uniqueness, and you should explain what I mean by being unique. Okay, so what I mean is that well, we want to prove that. So there, we know by our by our Axiom 3, there is a 0 such that x plus 0 equals 0 for x in V. And let's say there is another 0 in our vector space, so there is some z that also satisfies the 0 property. So it has x plus z equal to x for x in V also. And we want to show z equal to 0. So really we want to string together a whole bunch of equality such that z equal to the 0, where this 0 is this exists 0 that we are given from Axiom 3. Okay. And so this is really simple. So we start with z, and then we say z equal to z plus 0 because this is a property of 0. 0 plus any any vector equal to 0. Okay, and here we are doing extra careful. Okay, so z plus 0, actually we need to use our property A1 to show that it's 0 plus z. Okay, yeah, because if you don't have A1, you cannot just say z plus 0 equal to 0 plus z. Okay, so we need A1, so we have z plus 0 equal to 0 plus z. Okay, and then finally we can use our assumption. We say anything plus z equal to that thing back. Okay, so now that x is 0 here, so 0 plus z equal to 0 vector plus z equal to 0 vector. Okay, and so now we string together this equality, and well, equality sign is still what you think about equality sign. Equality sign is transitive. So you have everything string together with equality. This means this z equal to this 0. Okay, and yeah, so this is a proof that 0 is unique because if you have everything that satisfies the property of being a 0, then equal to the 0 that's given, equal to any other 0 basically. Okay, and yeah. And also here we see that A1 is important here. I guess you can show that if you don't have A1, then 0 is actually not unique. Okay, you can construct something something that's almost a linear vector space, but don't have A1 and don't have a unique 0. Okay, any questions so far? No. Okay. If we are okay with 0 being unique, then now it's easier to prove this scalar x multiplying any vector equal to the 0 vector. Okay, and okay, and the important part is actually something we kind of don't understand why it exists. It's this A8. Okay, so it's 1 times x equal to x for x. Okay, so we start with A8. So why is it important? Because now you look at all these equations. This is the only thing where one side has a scalar multiplication and the other side don't have. Okay? If you look at all those formula, those formula don't have any scalar inside. And all those three side formula has a scalar on left hand side and also scalar on right hand side. Okay, but you look at this equation, it has a scalar on left hand side and no scalar on right hand side. Okay, so you need something to some property to connect from something with a scalar multiplication and something don't. Okay, and that's why we must have A8 to our vector space definition. Okay, so we start with this A8, and we have x equal to scalar 1 times x. And then we're doing the smart part. That's actually none of the assumption we have. We just do scalar addition. So 1 is the real number 1. So we just have, we know real number addition, real number 1 equal to real number 1 plus real number 0. Okay, and this is the smart part. And oh, sorry, I guess this is also still a rule, but oh no, sorry, yeah, I'm going to face. Okay, so smart part is just write 1 as scalar 1 plus scalar 0. Okay, and now we can start using our rules to make this. Okay, start using our rules. So we have our distributive rule A6. So this alpha plus beta times x equal to alpha x times beta x. So we have 1x plus 0x. Okay. And now we can use our A8 again and turn our 1x back to x. Okay. And so in the end, we have that for all x equal to x plus 0x. Okay. And let's see this once again. So why is A8 important? Because if you don't have A8, you cannot go to x here. So you just have 1x plus 1x plus 0x. But then now you are not for x, you are just for 1x, 1x equal to 1x plus 0x. Okay? But with A8, we have that for x inside our vector space, that's x equal to x plus 0x. And now we compare these two things. I guess I still need to write this. Okay, so in the end, we have x equal to, okay, now I'm getting lazy. I don't want to write both ways with this drawing, so let's write vector sign. X vector equal to x plus 0x. And then we see that then this 0x satisfies the definition of being a 0. Okay, so for all x plus 0x equal to x. Okay, and so 0x is a 0, and so 0x is just like a z above, and we say every z is equal to 0, so 0x equal to this 0 in this existing of 0 here. Okay, any question? Yeah. So this is a derivation of about this abstract property of abstract vector space. So we derive two things about 0. First is 0 is unique, and second is that if you do scalar multiplication 0, then then you get the vector 0. Okay. Okay, and so we are done with 0, and now let's do inverse. First, we prove that inverse is unique, just like before. And okay, so to prove inverse is unique, we have we use we assume that so I guess it's just like before. So we have every vector x. And we know there is inverse minus x, and let's assume there is some y that's also an inverse of x, so x plus y equal to 0. Okay. And what we do is we start with minus x, so this minus x is the inverse that is given in this assumption, in this Axiom A4. And so minus x, then we can use xn3 to add a 0 on it. And yeah, but property of 0 minus x plus 0 should still be minus x. Okay, and then we use our assumption here where 0 is also equal to x plus y. So minus x equal to minus x plus y. Okay, and once we have this, we just use associative rule So minus x we copy here, and we use the associative rule to go from this thing to this thing. Okay, so we have a small arrow here. Okay, yeah. So we have minus x plus parentheses x plus y. We go to parentheses minus x plus y, and then here I guess technically. Yeah, technically we need to, if we are really careful, we need to do another A1 here, okay? So if we are very careful, because the minus sign only defined on the left side, so we need to have, we need to use A1 again to switch this minus x plus x to plus x to x plus minus x, and this becomes 0, okay? No, sorry, I'm still missing something here. So this is A1, A4. And yeah, so that's 0 plus y, and it's really annoying. I think I'm not sure whether we can. Yeah, there's something for you to think about, whether we can get rid of A1 in all these proof. But for now, let's use a whole bunch of A1. Okay, and so we get A1 here, and use A1 here to make this 0. And then we use A1 again to make it 0 plus y, y plus 0. So, and then we use A3. No, this is ugly, sorry. So let's get rid of parentheses here. Okay, and yeah, finally we use A3 again. So anything plus 0 equal to anything, so that equal to 1. And so this is what we get. What do we want? Sorry, this is what we want. We want minus x string together to y. Okay, so minus x and y here. Okay, minus x equal to y for y that satisfies x plus y equal to 0. Okay, so that's the uniqueness of inverse of every element. And finally, we can prove that minus 1 times x equal to minus x. Okay. And and just like before, we want to have we want to first show that minus 1 times x satisfy the inverse property. So anything times minus 1x equal to itself, and we can do this. We can just do this by starting with well, we're starting with the first identity without proof. So 0 equal to 0 times x, and now we have the smart move again here. So we have the smart move here where we break 0 into scalar addition. So 0 equal to 1 plus minus 1. This is just scalar addition. It's not any of the this is a property of scalar addition. It's not property of any property of the vector space. Okay, so 0 equal to minus 1 plus 1 plus minus 1. And then once again we use distributive rule, so this is equal to 1x times plus minus 1x, and we turn 1x equal to x again, and yeah, so and so we have x plus minus 1x equal to 0. So we have the starting point here is 0, and end point is x plus minus 1x equal to 0. And yeah, and yeah, so you see minus 1x is also inverse of x. Okay, that's that might be different from minus x, but because of the second thing says that the minus x is unique, so minus 1x must equal to minus x. So it's like we have minus 1x as y, minus 1 and the x vector, and it's like the y vector. Okay, so yeah, so this is very mathematical theorem where we use all those abstract manipulation to prove a very abstract rule about abstract vector spaces. Okay. Once again, if you just use your vector space Rn, which you do most of the time, you don't really do this so hard. You can just write down elements of Rn, and you can prove this very easily. Okay, so you just have say if you are in R2, and everything is like an element and an element. You do scalar multiplication 0, you immediately see the vector becomes 0, 0, and that's the 0 vector. Okay? But it's still nice to learn about how to do this abstract manipulation, because I think even for you in computer science, sometimes you will use a more generalized vector space. Say you might get a vector space with other scalars. Say the scalar is not real, maybe a complex number, or sometimes the scalar is in so-called F2, just 0 and 1, etc. And yeah, so it's nice to have the ability to do abstract multiplication when you are dealing with more exotic vector spaces. Okay. And yeah, I think that's all I want to talk about today. So we will just go to the checklist of 3.1. So we have vector space that we talk about basically just three things here. So we talk about this Euclidean space Rn. Okay, and then we have the abstract definition of vector space. It's a set of things, and with two rules, so the addition rule and the scalar multiplication. And they need to satisfy the closure rule and the extends A1 to A8. And then we have the theorem 3.1.1 that give us four things. So we have uniqueness of zero vector, and we have 0 times anything equal to 0 vector, and we have the uniqueness of the minus vector, and we have -1 of any vector equal to the minus vector. Okay, and yeah, I think we can stop here. And any question? Otherwise, we can stop 1 minute earlier today. Okay, so yeah. See you actually next Monday. Okay.